Hello, everyone. My name is Mark Hurlstone. I'm a lecturer in the Department of Psychology here at Lancaster University. And in my talk, I'm going to be focusing on the international negotiations on climate change. And I'm going to be talking about some work that I've been doing with a colleague, Ben Newell, at the University of New South Wales in Australia. We've been conducting experiments in the laboratory using cooperation games to try and simulate kind of basic aspects of the international negotiations on climate change in order to identify the kinds of variables and factors that might promote and hinder cooperation between countries. And so I'm going to report the results of just one of these experiments and talk about the implications for the climate negotiations very briefly. So what we kind of think needs to change in those negotiations based upon these results. So just as an inroad into my talk, I want to try and give a very brief overview of the international negotiations on climate change, which have stretched back now for 28 years. So these negotiations started back in 1992 with the establishment of the United Nations Framework Convention on Climate Change. And today, more than 200 countries have signed up to the Framework Convention. So most countries have signed up. To sign up to the convention is basically to endorse Article 1 of the Framework Convention, which states that it would be desirable to stabilise greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. So the negotiators recognised very early on that if they could identify a threshold for dangerous climate change, that might be a very powerful mechanism for encouraging cooperation amongst countries in order to reduce their emissions. And so much of the past 28 years of negotiations on climate change have in large part been about the search for a definition of what exactly constitutes dangerous anthropogenic interference. So what is dangerous climate change? What would take us there? And the negotiators had to wait a very long time to provide a provisional answer to that question. So the first attempt at an answer came in a meeting in Copenhagen in 2009. And it was in that meeting that an agreement was reached as part of an agreement known as the Copenhagen Accord, that in accordance with the scientific view, global temperature should be below 2 degrees, and that's relative to pre-industrial levels. So according to the scientific view, as espoused in the Copenhagen Accord, if we keep global temperature below 2 degrees, then we're safe, catastrophe is avoided. Whereas if we breeze past 2 degrees, then catastrophe will occur, so dangerous climate change will happen. Now, a year later, at another meeting in Cancun in Mexico, some uncertainty creeped into this judgment about the threshold for dangerous interference. And the negotiators spent a lot of time discussing the possibility that, well, perhaps actually we should be aiming for 1.5 degrees rather than 2 degrees. And that uncertainty then creeped into the most recent agreement, which hopefully most of you are familiar with, which is the Paris Agreement negotiated in 2015. And so the Paris Agreement is the latest agreement. It basically reaffirms the Copenhagen Accord. So we're still working towards keeping global temperature rise well below 2 degrees. But in addition, the Paris Agreement notes the desirability of pursuing efforts to limit the temperature increase to 1.5 degrees. So that's where we're at. Now, the important thing that you need to understand about this set of agreements is that it's the fear of crossing a dangerous threshold and the consequences that will bring, which provides the enforcement in these agreements. So it's Mother Nature's threat to tip a critical geophysical system that provides the catalyst for countries to reduce their emissions. That's the incentive. And that's how these agreements were strategically created, from the inception of the Framework Convention on Climate Change. But whether these agreements will actually be effective or not depends very much on the credibility of that 2-degree target. Now, according to the Copenhagen Accord, 2 degrees was chosen, quote unquote, based on the scientific view. Now, the question that I'm going to pose is 2 degrees really the scientific view? And since I've posed the question, you've probably anticipated that the answer is no, and it's a resounding no. And I don't want to discuss this table in too much detail, but basically what I'm showing here is estimates of the critical threshold from various scientific studies for various critical Earth system components that are kind of crucial for the climate system. So these are estimates for preserving these Earth system components. So things like the Greenland ice sheet, the West Antarctic ice sheet, the North Atlantic thermohaline circulation. So these are kind of, vital Earth system components for the climate. And what you can see in the column on the rightmost side is that there's a lot of variability in the temperature estimates for those different thresholds. So there's no consensus regarding, what the critical threshold is. And there's even less consensus regarding a kind of overarching critical threshold for dangerous climate change more broadly, like the 2-degree target in the contemporary climate negotiations. So the upshot of this is that if you look in the literature, one thing is very clear. There is certainly a consensus that dangerous climate thresholds do indeed exist. And there are multiple dangerous thresholds that we'd be concerned about crossing. But there's no consensus that 2 degrees is the location of the dangerous threshold. Now, what I'm interested in is, what are the implications of this scientific uncertainty for the international negotiations on climate change? So what impact will that have on the behavior of countries? And that's not a question that we can easily answer by looking at the negotiations as they're unfolding. So we are playing a climate coordination game under threshold uncertainty, but we don't have the counterfactual scenario available. We can't compare it with another world where the location of that threshold is known with certainty. Okay, the curtains are closed on that and we can't open them. But what we can do is we can run experiments within the laboratory that try to recreate aspects of the climate negotiations. And we can compare these different worlds and we can draw back the curtains and we can see what the consequences of things like threshold uncertainty are on the likelihood of something like the Paris Agreement actually being successful or not. And so that brings me on to the so-called dangerous climate change games that we conduct in the laboratory. So how do these games work? Well, basically, typically what you have is we have groups of 6 players, and each of those players gets given a personal endowment of $40. Now, there are some analogies in this game. So the players are meant to represent countries, okay? And the personal endowment of $40 is kind of money that they can spend on climate protection, okay? Now, the game's played over 10 rounds, and on each of those rounds, the players have to decide whether to contribute $0, $2, or $4 into a so-called damage prevention account. Now, we use a very neutral frame in this game. We don't mention anything about climate change, so we don't call it the climate catastrophe avoidance account, for example. And what the players know is that by the end of the game, the total contributions into this account must equal or exceed a threshold amount, okay? And what varies is the certainty or uncertainty of that threshold amount. So sometimes the players are told what the threshold is. So they're told that, with certainty, the threshold is $120. That's what you have to aim for. Whereas sometimes the threshold is uncertain. So it's a value that ranges between 0 to 240, and each whole dollar amount has an equal likelihood of being selected. But you won't know until the end of the game what the actual threshold value is. That'll be determined by a random draw. And hopefully it should be clear that, this threshold is meant to be an analogy for the global temperature threshold in the real game of climate change. Now, if the threshold isn't reached, so if the total contributions don't reach or exceed the threshold value, then catastrophe occurs, quote unquote. And what happens is that any remaining funds in the players' operating funds get reduced by 90%. So they almost get wiped out, basically. And that's supposed to simulate the kind of catastrophic economic loss of climate change. Now, there are two additional features in this game. So at the start of the game on round 1, and then again in the second half of the game on round 6, the players do two things. They submit a non-binding proposal and a non-binding pledge. And the proposals are basically, they have to decide what is going to be the collective target, how much are we going to contribute to the climate account. So hopefully, under the certainty scenario, they should say, let's aim for 120, because that is indeed the known threshold value. Once they've done that, they submit what are called pledges. Now, if you know the Paris Agreement, in the Paris Agreement, the countries have submitted their pledges regarding, how much they're going to do to reduce emissions to reach that 2-degree goal. And that's basically what they're doing in this game. They're saying, this is how much I'm going to contribute towards reaching the collective target that we've just agreed upon. But they're non-bindings. They don't, they can go against those pledges should they wish to. Now, this is the result of an experiment by Astrid Dannenberg and colleagues. It's a bit more busy, these results, than they need to be. So what I'm actually showing is the percentage of successful groups in 2 treatments, one where the threshold is known with certainty, one where it's uncertain. And this is for different hypothetical threshold values. But the only one that really matters is this one. So a threshold value of 120. So remember, that's the actual threshold value in the certainty treatment. It's also what we call the expected threshold value in the uncertainty treatment. So it's the midpoint in this uncertainty distribution, which varies between $0 to $240. If we were to run the experiment many times, then on average, the threshold in that treatment would be $120. That's why it's important. But the key result from these experiments is that, so if you look in the case of this particular experiment, in the certainty situation, groups avoid catastrophe all the time. So all of the groups manage to avoid catastrophe. Whereas in the uncertainty situation, what you find is only 20% of the groups manage to avoid catastrophe. So these results confirm that threshold uncertainty is a major handicap to cooperation. And this isn't an isolated result. It's been reproduced across a number of different studies. So what are the implications of these results? Well, the implication is that it's not the number noted on record that matters, so the 2-degree number in the Paris Agreement and the Copenhagen Accord, but what the negotiators know to be true, which is that the threshold is deeply uncertain. And they know it's uncertain because they negotiated it, okay? So it's really just a political tool more than anything else. And so the vulnerability in the current negotiations is the credibility of the science, so specifically the credibility of the science of locating the critical threshold. So an obvious kind of, follow-on implication from this is that if we could somehow reduce the uncertainty about the location of the threshold, then perhaps that would produce the behavioural transformation needed in order to help us prevent a climate catastrophe. And so what's the prognosis, for that actually happening? Well, it turns out that there is an emerging kind of strand of the climate sciences that is taking very seriously the prospect that we might be able to identify early warning signals of approaching climate tipping points. And so the idea is that in complex systems like the climate, they often exhibit so-called bifurcation tipping points. And as you approach that tipping point, so as you reach the point where you might enter as the system might enter a new regime, it exhibits a phenomenon called critical slowing down, where the state of the system becomes increasingly more similar to its earlier previous states. And this kind of critical slowing down can be detected using statistical techniques. So there's a very real kind of hope that perhaps these early warning signals might provide a kind of early detection system for foreshadowing a potential climate transition. They might, in short, provide the reduction in threshold uncertainty needed in order to produce this kind of behavioural shift to greater cooperation towards preventing a climate catastrophe. That's the theory, of course, and what we're interested in is what the data says. And so in the study that I'm going to describe, what we did is we took a dangerous climate change game, and what we wanted to do is experimentally examine whether such early warning signals can increase the likelihood of avoiding catastrophe. And the other important thing that we looked at is we varied the degree of precision of the signal. So clearly, it goes without saying that the uncertainty, needs to be reduced to some critical level, presumably, in order for it to have an effect on behaviour. And so we were interested in how much do you need to reduce that uncertainty for it to make a material difference. Now, this is a basic overview of the experiment, and I've already actually delivered a lot of the details about this experiment because it's very close in form to the experiment by Astrid Dannenberg and colleagues that I described previously. So we have 4 conditions or treatments. I'm going to refer to them as treatments. And the first 2 treatments are the ones that I've just described to you previously. So T1 is the certainty treatment, where the threshold is $120. T2 is the uncertainty treatment, where the threshold varies between $0 to $240. These are our kind of best conditions. And there are 2 additional treatments, right, called T3 warning wide and T4 warning narrow, which are our early warning signal treatments. Now, these are, up until the midpoint of the game, exactly the same as T2. These groups of players are told, just like those in T2, that the threshold is some value between $0 to $240, but they won't find out until the end of the game. And then, surprise, surprise, what happens is at the midpoint of the game, before they have to submit their second set of non-binding proposals and pledges, they're given new information about the location of the threshold. So in T3, they're told, actually, the location of the threshold is now somewhere between $84 and $156, okay? And that amounts to a 70% reduction in threshold uncertainty. Whereas in T4, they're told it's now between $108 and $132, and that corresponds to a 90% reduction in threshold uncertainty. So that's a very considerable and potentially unrealistic level of reduction, I might add. And we have 10 groups of 6 players in each of these treatments, so 60 players per treatment, 240 altogether. Okay, so I'm going to show you a number of different results. What I'm showing you now is the average contributions to this so-called damage prevention account, averaged across the groups for each of these 4 treatments. Now, let's focus on the blue bars first. What we're looking at here is the contributions of rounds 1 to 5. And what you can see is that for the first half of the game, contributions don't vary much. Okay, there's a little dip in treatments T2 and T3, but it's not reliable, okay? So what happens over round 6 to 10? So these are the red bars. So in the early warning treatments, T3 and T4, this would be when the early warning signal has arrived, okay, and they've been given this new information about the location of the threshold. Well, contributions remain high in T1, the certainty treatment. They drop down now quite markedly in T2, the uncertainty treatment. In the warning wide treatment, so where you get this 70% reduction in threshold uncertainty, they increase a bit, but they increase much more substantially in T4, which is this warning narrow treatment where the uncertainty reduces by 90%. So contributions are actually numerically higher than in the certainty treatment T1 in this condition, although not reliably higher. So that's all looking pretty good so far. Now what I'm showing you is the actual probability of avoiding catastrophe across those 4 treatments. So just to clarify what I'm showing here, the blue bars represent the average probability of avoiding catastrophe in the 4 different treatments. These red dots that you can see correspond to the actual probabilities for each of the groups. And remember, there are 10 groups in each of the treatments. There should be 10 dots for each treatment. And so what you can see is that they're very good at avoiding catastrophe in T1, the certainty treatment. So 90% of the group, so 9 out of 10, successfully avoid catastrophe in this treatment. The same isn't true in the other treatments. So in T2, the uncertainty treatment, it drops down to 42%. it drops down to 38% in T3. So that slight increase in contributions that you saw on the previous slide, that doesn't make much of a difference. And then in T4, what you find is that it does make more of a difference. So it's now risen to 61%, but there's clearly a big gap between 61% here and 90% here. Okay, so there are limits to what an early warning signal can do to spur cooperation, even when it reduces uncertainty to within 10% of the location of the threshold. Now, there's one final piece of data I just want to quickly show you. So what I'm showing you here across these 4 treatments is the average proposals, pledges, and contributions across those treatments. Now, remember that proposals and pledges, these are given on 2 occasions, on round 1 and then on round 6. So at the start of the game and at the midpoint. What I've done is, because they don't differ between those 2 time periods, I've just taken the average, and it just makes it a bit easier to see what's going on here. But what you can see is that when the threshold, one more thing, I've rearranged to confuse you the data on the x-axis, the horizontal axis here, so that uncertainty increases as you move from the left to the right. So T4, which is the early warning signal, which reduces uncertainty by 90%, is now here after T1. Whereas T2, whereas uncertainty is at its highest, is on the rightmost side, okay? Now, if we look at T1, first of all, what you can see is that proposals, pledges, and contributions are almost perfectly in line with one another. So people contribute consistent with their pledges, and their pledges are consistent with what they agreed would be the collective target. Whereas what happens is, as the uncertainty increases, you get this wedge between these 3 types of decisions. So proposals, pledges start to drop beneath proposals, and contributions start to drop beneath pledges. And that's at its most extreme here in condition T2. And if you wanted me to tell you, what is the history of, kind of the past 28 years of climate negotiations? Well, it's basically right there. Okay, it's right there. Countries have consistently proposed, to do less than they know they need to do to solve the problem. They've pledged to do less than is required to meet even those suboptimal targets, and they've also contributed less than is required to meet their suboptimal pledges. And that is 28 years of climate negotiations for you, I regret to say. And that's how the kind of Paris Agreement is trending right now. The other critical thing I just want to draw your attention to is that if you look in T4, what we had really hoped in this condition is that proposals would spike up to about 132, okay? Because to reach $120, right, that's a fair share investment of $20 per player, okay? But to guarantee that you'll avoid catastrophe with certainty, that is to conform to what scientists call the precautionary principle, you only need to make a contribution, a fair share contribution of $22 each. So raise your contribution by $2 and we can make sure that catastrophe doesn't occur. Only 2 out of the 10 groups actually do that. And so what you can see is that, despite the increase in cooperation, the increase in contributions, groups are they've got this great opportunity to avoid catastrophe with uncertainty, but they don't, and so that's something that we find quite worrying. I'm going to breeze through the rest of the talk pretty quickly. So there's some good news here, and there's also some bad news. And the good news is that an early warning signal that reduces uncertainty to within 10% of the threshold value did noticeably improve coordination, and reliably so. And group contributions rose to the expected threshold value, so that the same level that we see in the certainty situation. The bad news, however, which I just delivered on the previous slide, is that contributing that expected threshold value, that eliminates catastrophe, the risk of catastrophe with certainty in the certainty situation, but in the uncertainty situation, it still leaves a 50% risk of catastrophe occurring. And so the fact that more groups didn't contribute the upper threshold limit is really quite concerning, given that it's a very small amount of money. So early warning signals in general didn't sufficiently reduce the probability of avoiding catastrophe. Now, I'll just quickly note that there are some other issues with early warning signals. They may have limited predictability. They may be prone to missed alarms and false alarms. So we might miss an early warning signal, or we might think that we've received a credible early warning signal, but it's actually a false alarm. And worst of all, and this is a pretty obvious point to make, but early warning signals are, by definition, they arrive late. Okay, the time for action is now, right? Not as we're approaching an impending, climate threshold. So these are other, shortcomings with early warning signals. But what I think is very clear from this literature is that if we could identify a red line, a real red line for dangerous climate change, then the task of avoiding crossing that red line would be so much easier. But unfortunately, due to irreducible uncertainties in the science of locating these thresholds, this is really, it's unlikely that we're going to, get that reduction in the level of threshold uncertainty needed to produce the kind of behavioral shift. And so what we've argued based on these results is that what we actually need is strategic enforcement mechanisms that can recreate the incentives to cooperate that exist when the threshold is certain. So basically, if Mother Nature can't provide the enforcement, then the countries have to do so themselves. And that's the end of my talk. I'm sorry for being another speaker that's gone over the limit.